So in this video, we're going to talk about acoustics, and we'll start with a discussion surrounding sound basics. So first of all, what is sound? Well, sound is a mechanical wave that's caused by vibrations traveling through a medium. Now, when we say medium, we basically just mean the matter through which the wave translates. So for example, this can be a desk, a wall, a table, really any object, water, air. But the nature of that medium will affect how sound travels, because in general, sound travels fastest in solids, slower in liquids, and slowest in gases. And this has to do with the atomic structure or the molecular structure of different materials. So for example, in a solid where we have the atoms and molecules very, very close together, well, in this case, it's very easy for the wave to propagate. In liquids, which still have atoms in quite close proximity, but a little bit farther apart with respect to solids, the wave will move a little bit more slowly. And then lastly, in gases, as you might expect, we have the particles spread out much, much farther, depending on the pressure and temperature conditions. And in this case, the wave will propagate the slowest, because the distance between adjacent particles, that matter through which the wave will propagate, are farther apart. Now, as a wave, there are two important properties that we should know and understand specifically in the context of sound. And that's the frequency and the amplitude. Now, the frequency is simply the number of wave cycles per second, which we measure in hertz. But what's a wave cycle? So if we direct our attention to this top image here, we can see that we have the wavelength of this wave labeled. We have one wave, and we pick one position, and we measure the distance to the same position on the next wave, and that is the wavelength. So the more of these that pass a particular point per unit time, per second typically, well then the higher the frequency. And the higher the frequency, the higher the pitch. So by pitch, we're talking about a certain quality of the sound. So you can imagine a whistle has a very high pitch, whereas something like thunder has a very low pitch. So it affects the nature of the sound and how the sound is perceived by the listener. Then we have the amplitude, which in the context of a wave is simply the height of the wave from its equilibrium position. So for example, we here have that equilibrium position. The wave extends up and down the same distance. Well, that height, that maximum height, is going to be our amplitude. Now, this represents the loudness. So the greater the amplitude, the louder the sound. So we call the movement of a sound wave, of a mechanical wave, as wave propagation. But let's talk about propagation in a little bit more detail and also talk about a related phenomenon called reflection. So when sound waves propagate, let's imagine we have a sound wave moving in one particular direction, and we have some barrier in between. Well, depending on the nature of this barrier, the material this barrier is made of, the wave can do one of a few different things. It can reflect off this barrier and continue in a different direction. It can be absorbed by the material so that less is transmitted and less is reflected. Most of the energy of that wave is instead simply absorbed by the material. And then we, of course, also have transmission. So usually, at least some extent of the original sound will transmit through a material unless we're talking about dedicated soundproofing. So with that said, that reflection is what's responsible for echoes. Echoes occur when sound waves reflect off of surfaces and return to the listener. And if we want to talk about how this reflection works, it comes down to two main factors: how smooth or rough a material is, or how hard or soft it is. So smooth and rigid surfaces will efficiently reflect sound, whereas soft and porous materials will absorb sound and produce weaker reflections. So we can compare, for example, something like polished concrete to a polyurethane foam. The polished concrete is, of course, smooth and rigid, and therefore will reflect most of that sound, whereas the foam, being again soft and porous with a lot of air inside, this will absorb most of that sound. Now let's also talk about one of the most important fundamental phenomena or effects in all of basic acoustics, which is the Doppler effect. And the Doppler effect is the perceived pitch of sound changing based on the motion of the source or observer. So as sound source moves toward an observer, waves compress, which increases the pitch. We get more waves per second. But as it moves away, the waves stretch, which lowers the pitch. We get less waves per unit time. So we have an example here of a fire truck initially driving towards an observer before then driving away from an observer. When it's driving towards the observer, again, those waves compress. The pitch goes up, and that will have an effect on how it sounds from the standpoint of the observer. But then obviously, again, as it moves away, that wave stretches, and the result is we get a lower pitch. Again, this is more akin to thunder, whereas the initial case is similar to our whistle example. Now let's take a look at two more examples. The first example, we have a speaker and a listener which are separated by a barrier. In the left-hand case, we have a concrete barrier, and on the right-hand case, we have some foam. So let's consider how sound would propagate from the speaker to the listener in both cases. Well, in the case of a concrete wall, we're going to have the speaker speak. That will emit a sound wave which will reach the wall. Once it's reached the wall, it will strongly reflect. And the reason being is concrete is a rigid, hard, solid material and likely polished. So because of this, it has all of the characteristics for strong reflection, and most of that energy will be reflected. But unless we have perfect reflection, we're still going to have some degree of transmission, but the sound that comes out the other side is going to be of a lower intensity. It's going to be a quieter sound. Now, in the case of the foam barrier, we have something similar in one sense, but simultaneously quite a bit different. Of course, it starts the same. The speaker speaks, emits a sound wave, and that sound will travel towards the wall. But in the case of the foam, the sound will be strongly absorbed instead of strongly reflected. And again, the reason is because of the nature of the foam material. It's soft and porous. It has all the characteristics for absorption. So in the same vein, though, we're going to still have some degree of transmission, although again, it will be reduced in intensity. It will be a quieter sound. In our second example, we have a car chase. In the middle here, we have our culprit, our criminal, which is rushing away from the police. And then we have two police cars. We have police car A, which is moving in the same direction as the culprit, and we have police car B, which is moving in an opposite direction. So let's assume that everybody is moving at 70 meters per second. Let's consider whether A siren or B siren would be heard by the driver of this middle vehicle first. Well, in A's case, again, this is the vehicle that's moving in the same direction as the criminal. Well, in this case, you essentially have to subtract 70 meters per second from the speed of the sound, because the sound is being emitted, but the vehicle is moving away from that sound. Car B, police car B, is essentially the opposite case. It's moving in the opposite direction towards the vehicle. So this means the relative velocities are such that the speed of sound is actually effectively greater by 70 meters per second. So it's the siren from police car B that will be heard first, because those sound waves are moving in the opposite direction than the observer is moving. So let's summarize some of the most important points from this lesson. First of all, sound is a mechanical wave that's caused by vibrations traveling through a medium, whether that medium is gaseous, liquid, or solid. But depending on whether it is gaseous, liquid, or solid, the sound will travel at different speeds. And sound typically travels fastest in solids, slower in liquids, and slowest in gases. Then we talked about frequency and amplitude and said that higher frequency equals higher pitch. So we can think of a higher pitch sound as something like a whistle and a lower pitch sound as something like thunder. And then we said that the amplitude is essentially the height of the wave, and it's the intensity of the sound, and therefore greater amplitude is equal to greater sound. Then we talked about the Doppler effect, and the Doppler effect is the perceived pitch of sound changing based on the motion of the source and/or the observer. As sound moves towards an observer, the waves compress and the pitch increases. Oppositely, as sound moves away, the waves will stretch and this lowers the pitch.